So good morning, everyone. It's a pleasure to be here and give this talk in the International Day of Light. So we started with a philosophical, let's say, introduction to a very interesting phenomena. I'm just going to give a perspective talk, right? So I try to keep the very specific scientific detail low. And then, so I would like also to talk about our activities on this topic, which are at the moment happening at the Institute, because they are very recent and new, and maybe many of you don't know about them. So this is the title of a perspective article, which we just published, and it's going to show up soon. And that my talk is also about this topic, about the solar lasers. And why solar lasers, or why not solar lasers, or what was the problem since the beginning of the laser that there are not so many solar lasers around. So let's start by our problems on the planet Earth at the moment. One of them is energy, right? So if you look at the numbers, you see that the radiation that we get from the sun every day, that it hugs us, right? It's the presentation of life to human being. It's equivalent to the energy that can be produced by the whole oil reserved on the Earth. So just 1.5 days if you manage to capture this light. So the total energy that the whole world just consumes in 1 year, sun can provide this in 1 hour. And then if you look at our consumption, the way that we consume fossil fuel and generate energy that we need. So 80% of the energy that we need is generated by fossil fuel, right? And we know that by 2050, the demand of the energy is going to be doubled, and by the end of the century, the demand of the energy is going to be tripled. So if you look, you see that there is a tremendous energy which shines on Earth every day repeatedly, and we just let it go. So, how much we consume from this energy that comes to us every day, right? So if you look at the numbers, you see that only 0.015% of the solar energy is used for us to produce electricity, 0.3% for heating, and 11% of solar energy is utilized for the photosynthesis processes. So you see that plants also don't harvest the whole energy. Only 11% of the solar energy is used by plants to generate energy for themselves. And if you look at the green plants, you see that they only consume 0.5% or 1% out of this 11%. And most of the solar energy is used by algae and bacteria. Okay, so we have to use it, right? I think it's obvious to everyone, but now the question is why we haven't been using it properly, or what are the problems? So if you look at so there's a very famous, let's say, formula in physics, or a theory in physics, and that's called blackbody radiation. What blackbody radiation says, it says that when an object has a temperature, it radiates, right? And the hotter the temperature of the object, the radiation moves to a more and more visible light. So if you look at the temperature of the sun, it's around 5,900 Kelvin, and it matches roughly to this spectrum. So that goes up to the visible, and then on the other side also to the infrared. So this is the radiation of sun, which is emitted to the space. But what reaches to us is this curve that you see here, right? The blackish curve. So, and that's because simply we have atmosphere. So many molecules in the atmosphere just absorb the light and just puts these holes in the spectrum of the sun. To just give you a number, if you are in outer space, you get 1,400 watt per meter square sun radiation. And if you just move to Erlangen in the backyard, then you have around 600 watt per meter square. So the atmosphere, of course, you have some molecules, mainly the very, let's say, hard one is the water that absorbs and scatters a lot. And we have also clouds, right? That they just reflect and scatter the light and make our life tough to use this solar energy. Then what kind of light is that, right? Is it like a laser that is coherent in time and space? Very surprisingly, sun is not coherent temporally. We all know, right? It's like a bulb. Ah, it's this one. Ah, I thought it's from my microphone. I'm like, why I'm resonating so? And then, but very surprisingly, if you look at the spatial coherence of light, of the solar light, you see that it's partially coherent. So this is a very nice paper that maybe you can have a look later on if you are interested, that measures this coherence of light. And that's because just sun is really far away from us. What we receive on Earth are really these plane waves that reaches us. That makes it partially coherent, which is a good point, right? So now this is a tough game, right? We have atmosphere, we have absorption, we have clouds. Sun is not coherent, right? It's partially coherent in space. So what are the big whys that we can use it, or where can we use it at least, that makes sense to go to this battle and try to convert it to a laser, right? Which is a coherent light. So this is a graphic that we made, which I will discuss only 4 applications in this graphic that the solar lasers can really influence our life. One of them is a very simple one. We use photovoltaic cells, right? Solar panels to convert the energy of sun to electricity. And these photovoltaic cells, they absorb energy, just very specific spectrum of the sun. And they have like 30% efficiency at a very specific wavelength. So it's really hard to make them broadband and then use the whole spectrum of the sun that I showed you. And then there are some studies that people has shown that if you use coherent light and shine it to these photovoltaic cells, then you can increase the efficiency. So then in principle, if you manage to turn the solar light to a laser light and then shine it to the photovoltaic cells, then you have a better conversion efficiency, and efficiency is the problem of humankind, right? To have efficient processes. The other application is that, so there are so many hazardous zones that you want to reach and communicate to, but it's impossible, right? It's impossible to send electricity to some very specific places on the planet Earth. And the idea would be to just transfer the energy there by lasers, right? With very big mirrors, and just reflect the light, the light of the solar laser to that areas, and then convert them to energy there. The other application, which is very, at the moment, hot topic and important, is on sustainable cycles of generation of energy. So the topic that I'm going to talk to you is about this magic cycle, which is called magnesium economy. Maybe you've heard about hydrogen economy. It was a very hot topic for a while. But in principle, the idea is that you generate energy via chemistry, right? Clean energy. And these are all about how to make it sustainable and clean. So one of the economies, which is at the moment very hot topic, is magnesium economy. And that's because the magnesium is very abundant on the planet Earth. The sea and oceans are a very good source of magnesium that can be used. They are relatively light metal, so if one wants to transport it from position A to B for generation of energy, they are not very heavy, so it's possible. Most importantly, they have 10 times larger energy storage than the hydrogen. So if you can manage to run this magic cycle sustainably, then you also store so much energy. So what is this magic cycle? A little bit of chemistry. very fast. The idea is that if you combine magnesium with water, you release this much energy that you can use. Heat up something, use it, right? It's a free energy. Then this hydrogen, which is generated during this process, if you mix it with oxygen, you generate water, clean water, and you generate more energy. So you can use this energy and turn it to electricity also. What is missing? At the end of the day, you have to mix magnesium with water, then you generate MgO. So if you want to have a sustainable cycle, you have to bring back MgO to magnesium, in a way, right? Then you have magnesium that sustainably generates energy mixed with water and so on. And we know that magnesium, you can't find it alone in nature. It's always mixed. So in the ocean, it's also MgO all the time. So you need a process to reduce the magnesium oxide to magnesium. And that's when the solar energy, solar lasers come to play. So this is a method, I won't go through it, but you see that this is a magic cycle, and then to just reduce this magnesium oxide to magnesium, you need to put energy in your system. And then there are several Japanese groups and Toyota who are working on this topic, that if you use solar lasers to give the energy to these processes, then you have a complete sustainable cycle, right? You use solar laser, magnesium oxide from the oceans, and you generate water, heat, and again, magnesium to put it in this cycle. So this is one of the very big applications that people are very interested at the moment on solar lasers. The other one, which is actually followed by European Space Agency at the moment, very, I think, powerfully, is the idea of a solar, space-based solar power. So the idea was presented by a NASA scientist, I think in 1960s or 70s. And he did a very simple calculation. He has a patent on it, so if it works out, I think he's going to be a very rich man. So the idea was that instead of trying to convert the solar light on the planet Earth to laser, and then feed the photovoltaic cells and all these stories that I told you, it makes sense to just do this conversion in the space. Because then we don't have days and nights, right? There is no cloud atmosphere. You can have a 24/7 source of energy. And the idea was to just capture the solar light in a lower orbit, in one of the spacecraft in the lower orbit of the Earth, capture the solar light, convert it to laser, and shine it to the Earth. And then on the Earth, you have some converters, right, that convert the laser light to energy. But at that time, when they did the math, they saw that, okay, the conversion efficiency of solar lasers is really low, right? And then if you do the numbers with how much money you need to put the solar laser up in the orbit and how much energy you get, it was like, no, it won't pay off somehow. But if you look at some cartoons, for example, this Future Boy Conan, which is a cartoon and series that you can find in YouTube, you see that people were elaborating on it, right? So these are people in one of these space stations, and they are trying to put these photovoltaic cells, arrange it to the sun, to shoot with a laser to the planet Earth. So then, because of exactly this hassle that we have with the energy problem, then ESOC came in, and then they thought, okay, lasers are not efficient. Let's do it the other way. Let's capture the solar light in space, turn it to gigahertz, right? Do microwave. Turn the light to microwave, then shine the microwave to the planet Earth. What is the catch? You have 80% conversion efficiency of solar light to microwave. So then you can beam it from space to the Earth. What is the problem? Microwave is a very long wavelength, right? So the diffraction limit of microwave is huge. And when it reaches on the planet Earth, then the area that you are going to radiating is going to be 10 kilometers squared. And I'm pretty sure you don't want to pass this region, right? No one wants to walk, right? And then you ecologically, you are going to change the planet Earth. I don't know, the plants are going to be hurt and so on. So this is the idea that at the moment is followed at European Space Agency. Although we know that the diffraction limit is so high and so on, but we have problems with energy. So if you manage to get an efficient solar laser, then this area that you have to shine on the planet Earth is going to be 1 kilometer square or below 1 kilometer square. So it's very manageable, right? And then there are some scientists in NASA and the US that they showed that they can really point a laser from space to a very specific, because then you have to position also, right? We have also the positioning technology, so it should work out. But of course, the problem is that the solar lasers are not efficient yet. So then I thought it's cool to show you this picture. This is the first solar laser, solid-state solar laser. It's very interesting because you can see the scientists. That's how people published before. You could put your picture with your device in the journal, right? And then you see that it's, the laser is on one of these telescope trackers, right? Because you have to track the sun. Sun moves, right? And then Young, in 1966, he could generate 1 watt of laser just by engineering of these solar lasers based on neodymium YAG, which is a very common laser gain material. So just for you to know, laser was invented in 1960. And the first liquid solar laser was demonstrated in 1963. The first solid-state solar laser in 1966. You see that people got it fast, right? That, okay, we can use the energy of the sun. But if you look at how things moved, you see that, oh, the graph is really sparse, right? Not so much activities. Because then at that point, very soon, laser scientists learned that they can use another laser to pump the laser, which is much easier, right? It doesn't move, you don't have to track it or something, and you get a more efficient, easier life in the lab, and then they stopped to work on this topic. Until year 2000, and then you see that the dots are just increasing. And that's because the energy crisis that we have. People are back to the topic and try to make it better, make it more efficient, and make sense out of it. So if you look at this graph, it shows you that how much of solar radiation was gathered or focused to the gain material, and people could generate up to 100 watts output at the moment, right? But if you look at this curve again, you see that in the beginning it was very exponential, right? A very small change made a huge difference, but now it's quite saturated, right? It means that the design, the gain media, whatever, the way that we think it reached is optimized, right? So you need a new idea to bring in to change the state of the art. So all the lasers are also CW lasers, right? They work in the continuous wave. And if you look at other gain material that they exist, then you see that there are some that absorb in a broader spectral range of sun, and they can give you, in principle and theory, short laser pulses, right? But these are none of them are demonstrated because it's a challenging task. So, what are the main issues at the moment? One of them is the conversion efficiency, which is really low. And you can see that's because also we use very narrow spectral components of sun to convert, right? The other thing is that there is this very famous problem with the solid-state lasers, that they generate heat, so you have to cool it down actively with water or something, and that's really tough, right? Because you put energy, then you have to put energy on the system to cool it down, so it's not very sustainable. And then it is so hard to collect the solar light, right? Because it's incoherent. So you cannot put a nice lens and get a very beautiful focus. You have to fight a battle. So these 3 topics are the topics that we are currently addressing in our institute. So this is a collaboration that my group has with a group of Flora Kunst, that we are now thinking that if we can somehow employ topological structure for the better collection of solar light, then in another project that we are collaborating with the group of Claudio Gines, we are thinking about alternative way of cooling the solid state lasers. And that's called radiative cooling, which means that we use the sun to laze the gain medium and also use the sun to cool it down, right? So this is the theory work that at the moment we are doing. We are doing a bit of experiment already on this topic, which looks very promising. And then we have the Apache project, which was just funded, and it's an EU Pathfinder program with 5 countries involved. And the Apache is a nature-inspired project. So the idea is that if you look at the leaf of a planet, they absorb 30% of the light, they harvest the solar light, and they transfer it to energy with a very high efficiency. During the photosynthesis process, that if you look at literatures, you see so many scientists were inspired by this process. So why it is very efficient? It's because of these aggregates that they are participating in photosynthesis process, these very giant molecules, that they are absorbing the light and pass it to the center of their arrangement. And there, during the photosynthesis process, some chemical process happens and the energy is generated and transferred to the plant. So what we are aiming to do is to have such a structure, such aggregates, and then that bring the energy of the solar light to the center. And at the center, then we are aiming to put a laser gain medium, right? At a very small, let's say, nano level. So what's the beauty of it? Then you have a easy collection of the solar light, and hopefully, I mean, at least on theory, on the paper, it seems that we need a very low threshold of solar light to laze, right? Then that's gonna hopefully address the problem with the efficiency of solar lasers, and it's also, on the other hand, very friendly for you to be used in space, especially if you use also kind of bacteria to laze. Okay, so with this, I would like to end my talk about solar lasers and wish you a happy International Day of Light.